This new app called Rocked, ROCKD. And so, for example, I just downloaded it and it uses my location. And what it tells me is some really good, useful information. So imagine, you're a citizen scientist or you're an ecologist or whatever, and you want to know more about your specific location, the physiography and the geology. You want to know all that stuff. What this app has got is it's got a little bit of everything. So one, it tells you the physiographic region that you're in, highland rim, interior low plateau. It tells you that. Then it tells you the age of the rock, Carboniferous. In this case, we're Mississippian. And it tells you the age of the geology, 342 to 338 million years old. And then it tells you all the different rock types that are part of this region, specifically at this location. Specifically, we're on the St. Louis limestone here. So if you walk out, dig down in the topsoil and hit bedrock, you're on St. Louis limestone. If you were to go below that point, however, you're also going to hit some other layers. So there might be a chert layer or a siltstone layer or a dolomite layer. It gives you the exact longitude and latitude, accurate to within 35 meters. It tells you your elevation, both in meters at 154 meters above sea level or in feet, 505 feet above sea level. And then what's cool about it is it's got stuff here for the fossils. If you want to know what fossils are for this region, you can look at it in map view. If you want to know the minerals of this region, and then let's try paleo. Let's go there. And so what you can do here is you can look at animated paleo maps that shows where Tennessee was during the Mississippian period. And you can do that for various points in time. So like right now I'm at, roughly 300 and something million years ago. But if I scale up toward, let's go that way, towards 750 million years ago, it's thinking. That's getting back about 1.5 million years after the close of, after the erosion of Rodinia begins to happen. Then it should bring me up a map that shows that point. So you can go anywhere between 750 million years ago and the modern time and see a map of where we are in Clarksville. Pretty cool app. Really, I think it looks like it's pretty swift. So it's thinking. It's not generating that paleo map, but I'll let you know when it comes up. Okay, where we left off last time. Let's summarize the key points because I felt like I came into class a little bit erratic last week, right? We talked about that, like a big old glacial erratic. And what is that again? What is that? Yeah, it's a boulder of various sizes it's actually carried by a glacier that got dropped by a glacier somewhere in the glacial zone. And then other forces might have brought some of those erratics south. Normally they don't move. Normally they stay put. But some of those erratics then, particularly those adjacent to the Mississippi River, were caught up in floodwaters, meltwater, and brought further south. And I actually had the chance to see some of these erratics last week in Jackson, Mississippi, which had been dug out of the side of a Lusk Bluff hillside in Vicksburg, Mississippi, way down, on the river. Okay, so what were the key points we talked about last time? Walk me through sort of a summarization of the major points that you got from last class period. Because I want to be clear on this. I'm giving you guys a lot of information, right? We talked about this bowl of cereal approach. I'm putting all kinds of stuff in this bowl of cereal. It's almost like a damn stew at this point. We got a big mixed vegetable soup. But what I don't want to do is I don't want to overwhelm you and get you off topic. And I want you to keep your eyes focused on what the story is. So what were the key elements? 3 elements, give them to me, of what the story was last week. Clayton?
1.2 billion years ago, you have the supercontinent Rodinia, and I think it was the Alleghanian orogeny created a mountain range that reached across that entire supercontinent and later broke up to form mountain ranges that are no longer geographic.
All right, you're on the right track. You had some factual errors in there, but that's okay. We're going to fix those. the key first point, let me even step back before the 3 points. What was the overarching question that I posed to you at it was the introductory heading of the first slide from the PowerPoint last week. What question do we want to answer, Matthew? It's sort of, kind of. What do we spend the last, all of the first month of class talking about? Ryan? Okay, so we cover rocks. Kiki, what else do we cover? Soils, Jacob. Rocks and soils we covered. What's something else we covered? Yeah, the different landscape types, right? Landforms, physiographic provinces, and we spent a good 2.5 class periods or better talking about what, Jaron? Ecoregions, right? So we were setting the scene. And then the purpose of last class was, now that we had set the scene on this landscape, Juliet, what did I want you to start following with me now? So from Tuesday's class all the way through another 2 or 3 weeks, now that we've told you what the landscape is, what's the next 3 weeks all about? It is about the different periods. That's true. But there's one central question.
Why does it matter?
Yeah, how do we get this landform? Like, how do we get this landscape? What are the processes that led to it, right? Laura, I hear you down in there. You sound like you're in a hole somewhere.
Uh-oh, I'm here.
I got you. Hang on. Let me see if I can get that volume up.
I
Basically, I can't find a way to get my volume up very well. So when you need me, you just yell real loud. All right.
Oh, holler.
Holler. Okay. All right. So we're talking about processes. Now back to Clayton's, what he was working to answer there is, what were sort of the 2 or 3 main points we were trying to answer in Tuesday's lecture? He started out with, well, let's start with supercontinent Rodinia. Okay. The supercontinent that no one remembers. Everybody knows Pangaea. Let's talk about Rodinia. It was there first, right? So roughly 1.2 billion years ago, up until about 0.8 billion years ago, which would be 800 million. And then we want to talk about the formation of that. You mentioned the Alleghenian orogeny, but I think you meant another orogeny. What is it called? The Grenville orogeny. Good. Sorry again to my people on the screen. I can't hear you. You sound like mice whispering down in the basement at this point. The Grenville orogeny, right? And that was the one that built up this giant mountain range that spread throughout many different continents on Earth. And then we talked about, how do we know? Where could you go see the Grenville orogeny? Do you remember anything about? If you want to go, there's 3 places we talked about here in the Southeast where you could go see bits and pieces of the Grenville basement rocks. Yeah, you go up to the Amphibolite Mountains around Boone, North Carolina. That's one. Give me another one, somebody. Jaron? Pine Mountain window, you bet. And by the way, it's got grasslands on that window. They're called hog plum glades, which I like. I like Pine Mountain. One more site. Where else would you go? Not the St. Francis Mountains. That's a little bit younger. Yeah. So now remember though, northwest of the Grenville Mountain orogeny, you have that Yavapai Mazatl basement foundation rock. And if you go northwest of that, you got the Canadian Shield, right? And we talked about the Slave basement rock. So there's other ones at the farther northwest you go, but we're focusing right here on the southeast. So I'm thinking about part of the Piedmont of North Carolina, Virginia. And I showed you a picture of a place called the Picture Creek Diabase Barrens. Diabase is a type of igneous rock, but those are like over around where, like north of Raleigh, North Carolina, up to about Richmond, Virginia, in that little area around the North Carolina, Virginia border. Okay, so after we talked about when Rodinia formed and how, and what kind of evidence we might be able to see today to know that, then we talked about, what was the second key point? Yeah, we began to and maybe before that, we wanted to know what was life like during Rodinia, right? So we talked about that. And then thirdly, to your point, Kiki, was what are other processes that led to the modern landscape of the Southeastern North America, like its distinctive coastline shape, okay? There was just, maybe even we could add maybe a fourth or fifth point. So the shape of the coastline was one thing that began to take shape all the way from the breakup of Rodinia. What's one more thing that we spent quite a bit of time at the end of class talking about last time? It's
Robins.
Say again?
Robins.
Grabens. Good. Remember we talked about grabens. I probably called it incorrectly grabens, but whatever. What's the correct term? I'm looking at Ken because he's a geoscience major, huh? Somebody look it up. How do you pronounce it? Is it graben? It probably is, or graben. But yeah, and so
We're
What-
grabbing for answers.
yes, you're graben for answers. Good, Laura. So tell me then about a graben. What's the significance to our discussion? As soon as you answer that, we're going to launch into today's lecture.
Gulf of Mexico, Mississippi River.
You got it. It helped determine the placement of the Mississippi River ultimately, right? Long, long time into the future. Okay, now, excellent point. Thank you for yelling it out. You'll need to continue to do that until I figure out how to get my volume back on track. Theo says, Dwayne, we are seeing the PowerPoint in presenter mode or whatever it's called. Well, I don't want you to see that like that, brother. So let me end the show. And let me see if I don't know how to, I'm getting there. Wait a minute. Use slideshow. That's what I want. How's that, Theo?
You got it, man. Thanks.
Got it. All right. So, we also talked about a little bit, and I went back for a new version of the PowerPoint I'm going to post online and added a slide about the Cambrian explosion. I don't feel like I did that very good justice. So I added just a slide to kind of represent that a little bit better. And that's really where today's discussion is going to take place. So with reaching the 550 million year mark, that represents the dividing point between the Precambrian era and the Paleozoic era. Remember, we're talking about the big level, right? Eras, E-R-A-S. We're on the Eras tour. Taylor Swift Eras tour right here. By the way, I went to see her in concert this summer. Amazing. It was awesome. Did you go to Nashville and see her? I went with my wife and my two daughters. God, it was really great. It was good. I'm a total Swiftie, I'm sorry, but it was amazing. It was amazing. So anyways, we're about to hit the eras tour, okay? So what are the eras that we're concerned with? Number one, Precambrian era. Number two, what you got? Paleozoic, the time of ancient life. What's the time of middle life? Mesozoic. Meso means middle, right? And in the time of recent life, well, y'all been studying your eras. Now we're going to do is kick off the first period within the Paleozoic era, which is the Cambrian period. Say it with me real quick out loud. Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian. Those are the ones we're going to go through that constitute the Paleozoic era, okay? So for Tennessee, yeah, Clayton?
Why do we divide the Carboniferous into two sub?
That's largely a European thing. So in Europe, European geologists primarily do not differentiate. They just tend to call it the Carboniferous. Since most of Western science evolved out of Europe, that's sort of a legacy of this Eurocentric classification. In America, we tend to distinguish between Mississippian and Pennsylvanian, as you can see by these two state names, based on the fact that those rocks were largely first described from rocks of those general regions, right? So that's an American classification, and that's a European classification.
Is there an event or something that draws the line between where one starts and the other begins? Or
Absolutely. Yeah. Yeah, every one of these has an event that separates it. It's a very precise, there's like a, I don't know, I don't know the name, because again, I'm a geologist in the movies only. But there is like a very rigorous classification breakdown. Like all of these periods that you see, they get broken down into a much finer level of classification that really stratigraphers and petrogeologists and paleontologists need to know those very, very fine scale divisions. And they have different geologic markers which define the beginning and end points of those. But that's kind of beyond where we need to be. Yeah. So for us then, remember that if you were to dig down a few thousand feet below the surface, you would eventually hit granite bedrock, even though we don't have igneous rock at the surface here. What is that rock called when you hit granitic bedrock beneath us? It's called the basement. And in this case, that rock is of what age? Well, loosely speaking, we say that they are Grenville aged rocks because they form from the Grenville orogeny. Now, above that granitic basement rock, we might have some Precambrian granites as well on top of that, or not. But when we start to get to the Paleozoic, the first rock we have of the Paleozoic is called the Cambrian. Throughout most of Tennessee and Alabama and Mississippi and Kentucky, the only Cambrian rock you really see is in over around Knoxville and Chattanooga. Here, Cambrian rock is well below the surface. So from Nashville, you'd have to dig down another few hundred feet before you get to Cambrian age rock. It's not exposed at the surface. Ordovician is exposed all around Nashville, and then we've talked about from there all the way up to like around Clarksville is Mississippian rock. If you want to get to Pennsylvania from here, you got to go up. Okay, so you can go over at the same elevation, like toward the Cumberland Plateau, and go up, in which case the top of the Cumberland Plateau is capped by Pennsylvania rock. Or you can go north of here, north of Hopkinsville, Kentucky, and the tops of those hills is capped in some cases by Pennsylvania age rock. Permian rock, though, remember that unconformity we talked about? Permian, Triassic, and Jurassic are all entirely missing from this region. There is a little bit of Permian rock in westernmost Kentucky, maybe West Virginia. Otherwise, you got to get over to like Texas and what they call the Permian Basin, which is a big fossil zone for certain types of reptilian reptile fossils, for example. But by and large, we're missing Permian, Triassic, Jurassic, and early Cretaceous rocks, this part right here. Okay? Now, on this diagram here, I've kind of indicated, we do want to occasionally point out what are some of the major evolutionary events that happen at the same time. Well, the thing with the Cambrian explosion, roughly 538 million years ago, is that it led to this explosion of the different organismal groups that many of you have studied if you've taken, biology 1120, and you're studying sponges and echinoderms and mollusks and gastropods and, all these different kinds of forms of life. Many of them originate back, or their lineages originate back at the time of the Cambrian explosion. Shortly thereafter, by toward the middle to end of the Cambrian, we do begin to see the very first evidence of spinal cord development. The notochord, if you are familiar with like animal morphology and anatomy. So the notochord begins to develop in some things. They don't have a true backbone yet, but we do see the first notochords. Basically animals with a head, animals with a spinal column. We also see the first fishes begin to evolve here. And all of these are preserved in the fossil record, which is remarkable. I would encourage you all, if you want to ever go see an amazing museum that basically walks you through all this stuff in real time, go to the American Museum of Natural History in New York City. They have probably one of the best exhibits of fossils, sort of in sequential order, that I've ever seen. Okay, so we're going to focus on the Cambrian for a little bit. Now, by the time we finished last class discussion, we were at that Precambrian end, 550 million years ago. Now we're going into the Cambrian period. And let me see if I can drag this off here at the bottom. I don't want to show that thing. Why is that? Can I minimize that thing? I feel like I'm having all kinds of challenges today. We just hide the floating meeting control. That's what I'm gonna do. Perfect. So, you know, there's not a lot of time difference here between these maps right here. Okay. So, on the left, you've got 540 million years ago, the early Cambrian period. I want you to notice that the continent of Laurentia, which is the ancestor to North America, is beginning to rift apart. Remember that term, rifting, R-I-F-T, right? The splitting apart of a continent. So as this continent is rifting apart, you have a new ocean basin that is developing right off of the shore. Now, this is not the current eastern shore that you think about. Take a look, for example, over here on the left, you've got the cardinal, the sort of compass. North is actually this way, right? That's the equator right there. So we would be approximately where Clarksville would probably be, I don't know, about where Ecuador or Brazil is today. And the continent is totally flipped upside down or up on its edge. Okay. So now, as this ocean is opening up, let's talk about that process just a little bit. When you're looking at these images, I want you to think about the different shades of blue and what they mean, because that really is an important part to kind of understand as you think about the tectonic forces that are happening around each continent. Number one, notice these areas here that are in very light whitish blue. Somebody just tell me, what does that mean? Those are shallow seas, right? Anywhere from probably, you know, single digit numbers, you know, a few feet all the way up to probably a couple 100 feet deep. All right, here is the edge of the continental shelf, right? This sort of, this pronounced edge here on the right. And then if you look into this zone, this is kind of the deeper ocean basins, maybe a few thousand feet deep. And then I want you to notice these very dark lines right here. Right? What are those? Those are your oceanic trenches, right? What's happening in the oceanic trenches? That's where we see geologic subduction, right? So one tectonic plate is diving down and is going down and moving underneath another tectonic plate. And as that happens, then you have volcanic activity that's often happening. So that one piece of crust is diving down so deep that it basically remelts. It melts. And in that melting process, then you may have volcanoes happening immediately adjacent to it. Do you see any evidence of that here? Yeah, those islands, right? Just like the Hawaiian Islands or a volcanic island arc, ARC. Here you have a volcanic island chain or an island arc right here. As that ocean basin is pushing down and diving underneath that other ocean basin, it's creating the volcanic activity needed to form these islands like the Hawaiian Islands. And so those are doing a couple things. Number one, those are places where species can live and colonize. But those island arcs are also moving, like the Hawaiian Islands are. They themselves get to move back and forth, or they follow tectonic plate movements. And they're also belching out ash and maybe lava. And that ash, in some cases, we're going to come to see, we actually have that ash preserved in the rock record right here around Nashville. You can actually drive down the interstate and see the layers of volcanic ash that come from these volcanoes. Not these, but we also see it in the Ordovician period. We see it from the Ordovician volcanoes that represent volcanic island arcs off the coast of Laurentia at that time. Now take a look at the map on the left and the map on the right. And what is the, number one, remember how we talked about that distinctive coastline of North America was forming at the end of the Precambrian? And it had to do with the way the American continent was rifting apart, right? That rifting action just basically tore all that stuff off, moving it farther and farther away, creating that distinctive notch that will eventually continued. Even after we build Pangea and break Pangea up, that notch is going to go on to continue to the present day to become the Gulf of Mexico. But I want you to look on the left and on the right. In just a span of 20 million years time, what's the biggest difference you see with regard to the Southeast on the map on the left versus the map on the right? So all these light blue areas here, okay, which are now basically ocean. If you go back in time, right, because 540 is older, then it was land. So what you're saying then is that the ocean has risen, right? All right, what do we say? There's a term, remember James, for when the ocean rises or the ocean falls. There's two terms I wanted you to know. What is that? What is it? What do we call it? Remember how we gave the example where you can have a road, like a cliff, and in that cliff you might have a layer of shale, sandstone, limestone, shale, sandstone, limestone. Those alternating layers. And we said that that's the result of the changes in sea level. What is it called when the oceans rise over a piece of land? Okay. Subduction? No, not subduction. That's when a continental crust goes underneath down in those deep trenches. Sarah? Kian? Almost. Juliet? Transgression. All right. Transgression is when the ocean levels rise, and when they fall, ocean levels fall. It's called a regression. Okay. So this is evidence of a transgression because we're coming forward in time. We're seeing the ocean levels rise over a large chunk of Eastern North America. We're going to call it North America, but you're going to know that I mean Laurentia. All right, so, and then it's covered by shallow seas. So what should we expect? If we find some Cambrian rock in Eastern Tennessee, what type of rock should it be? It should be limestone, or it might be, it could be, yeah, absolutely, they're Cambrian shales, or it could be what? You might have some, or dolomite, or chert. All of those can have marine origins, okay? Okay, now, before we move on, let's look at the diagram at the top. This is a bit complicated, and I want us to make sure we kind of are fairly comfortable with this before we move on. So number one, over here on the far left of the diagram at the top, this is the North American continent, okay? On the far right is Africa, okay? What we're going to try to do is talk about the stuff that's happened in the in-between. So number one, we have two ocean basins that are opening up. This is still a little bit confusing to me, okay? So if it's confusing to me, I'm totally understanding if it's confusing you. I don't pretend that we're going to have all the exact facts straight. We want to just get the general story. Y'all with me? Okay. So you have basically two ocean basins that are opening up, and they're separated by a volcanic island arc. We've already explained kind of how that island arc is there, right? Are there any examples that you can think of in the world where one ocean meets another ocean, but they're not separated by a continent? Any examples of that where two oceans come together, like just ocean to ocean and touch without a continent being in between?
Yeah.
Yeah, the Atlantic and the Pacific.
And where would that be at, Brandon?
It would be under South America.
Okay, got you. So down at the southern tip of South America where the Atlantic and the Pacific come together at the Straits of Magellan, okay? Good. Any other ideas? There's one more place where two oceans come together.
Indian and South Pacific?
Could be the Indian and South Pacific. Or where the Indian Ocean and the South Atlantic come together at the southern tip of Africa, right? But there's one glaring case where like three of the world's oceans all meet another ocean. How about the Southern Ocean? Y'all know about that one? That's the one around Antarctica. And the reason we call it the Southern Ocean is that it has its own ocean currents. And they basically circle around and around Antarctica. There's a circumpolar current. And those waters, while they're not physically separated from the South Pacific or the South Atlantic or the Southern Indian Ocean, they are, for all intents and purposes, considered to be a separate ocean, even though those ocean waters come right up against each other. There's not a whole lot of biotic interchange between them. So the reason I point that out is because it can be a little bit difficult when you're looking at this to understand that basically what you have here is the emergence of two parallel ocean basins that are kind of side by side. And what separates them is this volcanic island arc.
Yeah.
Okay. But we need to dig a little bit deeper and understand what makes an ocean basin an ocean basin. And here's the thing I want you to keep in mind. In these two ocean basins, so for example, let's just draw this, right? We've got this eastern shore of America here. It's actually the southern shore, like so. And then out here, we've got this, this volcanic island arc, okay? Over here. With an ocean trench along its western base. Something like that. And then, notice that I've got this double arrow right here. What does that indicate? Seafloor spreading, okay? So that means that this part of the ocean floor and this part of the ocean floor are spreading apart from each other. So what does that mean has to exist right through here? A divergent plate boundary, which we would call a mid-oceanic ridge. So you've got an open ridge line underneath the ocean basin that's generating molten magma. And that molten magma is hardening into what type of igneous rock? Basalt, good. And as that does it, it is pushing out sequentially the ocean floor on either side into parallel bands. And it's that push which is pushing the ocean floor wider and wider apart. And then right here, this tectonic plate that is pushing wider apart at this mid-oceanic ridge right here, or this ocean basin, is overriding this separate basin. So across that island arc, you have the same thing happening over here. You have another mid-oceanic ridge right there, right? And the seafloor spreading is happening. Molten magma coming out. And again, it's pushing new rock out on either side, like so, pushing against it. But this one is going under the other one. See that? Going down, subducting under the other one, which is leading to this volcanic island arc chain right there. I'm sorry for those of you who are on the computer, you can't see me drawing on the board. And then, of course, over here is Africa. So that's a little bit about what's happening right here. There's one last thing I want to throw in the middle, which is what they call the Piedmont terrain. And this is basically a big chunk of land that's sort of caught up out here as like a subcontinent or a microcontinent. Maybe imagine it's about the size of Madagascar or a small version of India. Okay, it's going to become important later. Why? Because it becomes the Piedmont today of the Carolinas and Virginia. All right, last thing, remember we've already talked about the Mississippi River Rift Zone is already firmly established here because of that failed rift. And that's why this area is low, and that's why the sea levels are able to protrude up into that low valley because it's already in existence at that point.
Question.
Yes.
I don't remember why you said that the rift failed. Is it because it didn't have any more distance to sink?
Yeah, I don't know exactly why. The question is, why did the rift fail? Rift valleys they sometimes fail, but I'm not sure as to why that happens. Sometimes they stop rifting apart
Oh,
And that, and so it becomes what's known as a failed rift.
thank you.
You're welcome. All right, now what I want to do is, let's come forward in time a little bit. So we're at 540, 520 million years. Now I'm going to put a new image up here on the right. And this is all the way at 500 million years. And now you can see a little bit more of a macro view. Notice those volcanic island arcs out there on the eastern, or out there on the edge of the coast. Look at how much of the Laurentian continent now is underwater by the year 500 million years ago. There are pockets, though, that are above sea level, like the St. Francis Mountains of Missouri, for example. The final thing I want to mention to you before we go on is we generally don't have any rock from the early Cambrian period in Tennessee preserved anywhere. We have late Cambrian rock, as I mentioned, in East Tennessee, mostly limestone, as Clayton suggested, and dolostone. But the question to you all, why do we not have early Cambrian rock? There's a clear reason if you look at these two images. That's called early Cambrian. This is middle Cambrian. We have middle and we have late Cambrian rock. But why not early Cambrian? You're getting there, right. In the middle and late Cambrian, we have a depositional environment, okay? It's receiving sediments, limestone ooze, or what have you. Fossilized marine organisms like, oyster shells and those kind of things. But in the early Cambrian, it's not a depositional environment at all. It's an erosion environment. Why? Because it's above sea level. It's an uplifted zone. So if it's above sea level and it's uplifted, then that means the forces of erosion are greater than the forces of deposition. Okay? So here, that land's actually eroding away. Nothing is actively being recorded or fossilized. Those soils and sediments are being washed away into the emerging continental shelf, which is beginning to develop out here. That's why we don't have early Cambrian rocks of this region. Okay? Okay. This is just taking a look back, because now what I want to do, now that we've kind of thoroughly taken a while to introduce some of those concepts, did me breaking some of those things down help a little bit? Because there's a lot of action happening, right? And we also have to think about this is happening in the span of worldwide dynamics. There's not just two continents moving, they're all moving, and they're all doing their own thing. Okay, so let's go forward. By this point, we're at still in the late Cambrian, 514 million years. So Rodinia has been broken up now for a good 300 to 400 million years. We're firmly now undergoing the Cambrian explosion. And by this point in time, I want you to notice that the continents that we today think about as Northern Hemisphere continents, which are North America, Europe, and Asia, right? Notice what they are. They're very small, relatively speaking. Laurentia is the biggest one. North America is the biggest one. But what about all the Southern Hemisphere continents? How would you describe them together? What would you say, Kiki? It's still a big old landmass, right? Yeah, they're not a necessarily the world isn't dominated by one supercontinent, but it definitely has a Gondwana. Y'all have heard of Gondwana land, I'm sure. That's what this is. It's the collection of Southern Hemisphere continents, all still one big continental landmass. They are a supercontinent, essentially. So as part of this, you've got Antarctica, you've got India, you've got parts of China. There's the Arabian Peninsula is there. That's Saudi Arabia. You've got parts of West Africa and South Africa, and here's South America. But notice where Florida is. Remember we talked about parts of Florida is actually part of Africa? It's right there. So that landscape that we won't even get, and look at where it's going to have to go from here and shift all the way around past what is now Europe to somehow magically collide with right there on future North America. So to get there, though, All this stuff right here is gonna have to begin to shift, and eventually these are gonna shift up into the northern hemisphere. This is gonna shift up with it. And let's keep one thing in mind, which is so far we've been talking about what have these ocean basins been doing? They've been spreading apart, right? Eventually, though, that's going to undergo a reversal. And those oceans are going to close, and those continents are going to move towards one another instead of being pushed apart. That sort of conveyor belt system or of tectonic movement is what drives the evolution of Earth, really. Okay. Okay, so these orange lines are subduction zones. Let's just highlight that one more time. And now what I want to begin to introduce to you is the next three orogenies that we need to think about. Okay. So after the Gondwanan orogeny, roughly 1 billion years ago, we go forward in time all the way into the latest Cambrian period, before we start seeing the very beginnings of the next mountain building episodes. The first one we see is going to be called the Taconic, sometimes called the Taconian or Taconic orogeny. All right, this is going to be followed by the Akkadian orogeny. Followed that by the Alleghanian. And my good friend Theo suggests that there's another one in here we might talk about called the Washita-Marathon orogeny. Now, arguably, you could kind of probably put all those together into one big, long, protracted mountain building process that begins in far northern Canada and ends in western Texas. As these various continents begin to collapse together, they start where far northeast Canada comes together with what eventually will be northern Europe. And that's the first part that kind of begins to build up under the Taconic orogeny. Yes.
I'm guessing that they're geological sucking. So in order to make these land masses go closer together, the ridge in between them producing the new land, the force of that is being overcome by ridges on the other side, pushing them in.
Help me out there. I'm not following you.
How do the continents move closer together? Are they being pushed from the outside?
What's
or
the
is something
force?
happening in the mid that's pulling?
What's the force that's doing the pulling? Yeah. To answer that question, what is the pull? They're being pulled essentially.
They are being.
They are.
Okay.
The pull is happening by the convection currents in the mantle. And so the core of the earth and the great heat generating force that it is causes temperature differences to build up within the mantle, right? And these exchanges of heat of molten metals like nickel and other kinds of molten nickel, iron and nickel and some others. That process of that fluid flowing motion has a drag effect. And it's dragging what we can think of as like ice cubes floating in the top of that molten magma, except it's continents floating in the top of that molten magma. And so that fluid motion of the upper levels of the mantle drags the continents above them in a direction. Okay. And that can shift and go back the other way. That's why we see the reversal of tectonic forces. Very simplistic, definition, but I'm sure we could get really deep on that beyond my level of ability to explain it. All right, so, but that's a great question and one that needed to be asked. Thank you. Okay, so the Taconic orogeny now, what I want you to notice is look at where Siberia is and look at where Northern Europe is. These eventually will come together to form Eurasia, right? Europe and Asia together. And together then, ahead of them, notice there's a fairly long distance out here. Eventually, they're going to begin to move closer to Greenland and northeastern Canada. And that's going to result in the beginnings of a mountain range right in here as part of that Taconian orogeny. All right, let's take a break from that stuff there for a second. Let me see if you have any questions. And then we're going to take a look at what was life like during the Cambrian period of this region and how do we know? Any questions about any of that stuff? Okay. Okay. So if we want to go back and look at those shallow seas that covered this region during the Cambrian, particularly the middle and late Cambrian, here's what that might have looked like. I apologize for the text being cut off here. This would have been a tropical lagoon. You would have had these warm, shallow seas. You would not have had, by the way, forest vegetation like palm trees on the land, because trees and even vegetation living on the land had not yet evolved. We don't even have land plants at this point. Now, some of these seas were so shallow that you can actually see this in some of the rocks that are still preserved, like in this piece of dolomite from Alabama. You can see areas here where there was a period of exposure of the drying of these shallow lagoons. You can imagine these are kind of open with the water levels are fluctuating. These areas are underwater. These areas indicate drying. So just one piece of evidence there of those fluctuating water levels. On the left is a geologic column. This is a typical sort of vertical rock profile like you might see around Knoxville or maybe Birmingham. And you can see the various types of Cambrian rock. And so at the very bottom here, we have some middle Cambrian age rock, the Conasauga Formation. Above that, we have what's called the Ketona Dolomite Formation. And then the Knox group, which contains different kinds of dolomites. These are all exposed in and around East Tennessee, in Alabama and the Ridge and Valley. And you can see the key to the rock types there in the very bottom. So these are mostly limestones, some cherty dolomite, and a little bit of shale in places. Here's what some of those rock types of these ancient seafloors look like today. And so here it is in up in northeast Alabama near Gunnersville Lake. And you can see those different rock layers of, in this case, some of the limestones of that area. Lime-rich tropical seafloors. These are from a little bit later of the Ordovician period. They still kind of show. Here's some additional Cambrian age rocks. This is all dolomite down in Alabama. A lot of this has been upturned by the forces of collision with Africa. You got things like trilobite fossils, these large sort of marine invertebrates. Some of these are about double the size of a quarter, but some of these were the size of your hand. Trilobite fossils also show up in places like the Canadian Burgess Shell, which is Cambrian aged. Now, trilobites they evolve for a time and then they disappear rapidly. So these are a totally extinct group of invertebrates. And then the Cambrian period, we talked about sort of the Cambrian explosion. Lots of different types of marine organisms evolved during this period. Things like star cobbles. These are from fossils from Alabama. In this particular type of sandstone, just south of Birmingham, more trilobite fossils. And then we begin to get into the later time period, Ordovician. And this is the time period where we have rocks of this age, which are right around Nashville, okay? So let's take a look and make sure this comports with what we understand. Here's Laurentia, right? Right there about is where Nashville, Clarksville is located. And you can see that pretty much all of the United States at that point, including all of Alaska, is underwater, and even a lot of Canada as well. Now, by this point in time, remember, we said that what is today's Europe is gradually moving a little bit closer. And look at Siberia. It's also moving closer to North America. So what you would expect when 2 or 3 continents move together, you would expect a collision and mountain building to happen. And that's exactly what we're seeing way up in here, places like Greenland and northeasternmost Canada. That's this Taconian orogeny or tectonic orogeny that I was talking about. So we begin to see the very first mountain building episodes affecting what is the northern Appalachians. Okay, notice the time period, 458 million years ago. let's begin to also look here at a couple of things going on. There's those two ocean basins we talked about earlier. Everything is shifting, so it's very complicated from where we started. Notice that Europe is kind of getting down in the middle, for example. There's the mid-oceanic ridge for the Tethys Ocean. And then here's the Iapetus Ocean, which is the ancestor to the Atlantic. Let's bring that down then, and take a look at this map right here. From the Middle Ordovician to the Silurian, this Taconian orogeny, you can begin to see what's already beginning to happen. We're beginning to see this ocean basin is going to start to close up a little bit. Now, I want you to also notice right here, here's where future New England is, along with Nova Scotia, Canada. Here's England, the country. And then this island here is called Avalonia. It's going to get sort of caught up in the action and will eventually become part of the Piedmont of North Carolina. A lot of complicated stuff happened. Notice Gondwana on the right is still relatively intact. And now what's going to begin to happen is this large landmass here, Gondwana, the supercontinent of all the southern continents, is on a collision course with these northern, what we now think of as northern hemisphere continents. They're all going to begin to move together. These two are going to move up. And then this is going to rotate. Africa is going to collide around. And it's all then going to begin to come into place and collide together right here to form the supercontinent Pangaea. But that's not happened yet. It's coming in the future. So again, there's the Taconian orogeny, where northern Europe is about to collide with northeastern Laurentia. And there's the future second orogeny of the two. The Acadian is getting ready to happen. Anybody here have been to Acadia National Park? You might know where it is. Where's it at, Jaron? It's in Maine. What's the significance right here of the Acadian orogeny with this little group of islands that you see right here? Yeah, and New England, Maine's part of New England, right? So part of why we call that the Acadian orogeny is it includes the landscape of Acadia. That's a French term for parts of eastern, that region, which includes like Maine and easternmost Canada. That's an area called Acadia. In fact, a lot of the people who would eventually go to settle Louisiana, the Cajuns, come from Acadia, which is the Maine and eastern Canada region.
I'm confused what's going on in the battle.
Mm.
I thought that was
Me too.
the arc between Laurentia and what now Baltica and Siberia, right? So now it's kind of rotated entirely out of position, but our diagram here on the bottom still shows it's separating Iapetus and Theocraic, which isn't even on this figure.
Exactly. There's a lot of complication for, yeah, number one, we're going to focus on Iapetus, but I can't even begin to tell you about Theocraic versus Paleotethys. So let's just all agree to let that one go. Okay. But yes, Avalonia, this very much gets complicated. And if you look on the various diagrams, there do seem to be some inconsistencies. Regardless of where it was, just know that landmass that eventually becomes the Carolinas is Avalonia. How it's diagrammatically displayed, because these all come from like 3 different sources over like spanning 30 years. So the science could have changed between the 3 sources a little bit too. But great question, and it's one that I have been puzzled over many times, but don't let that interfere with the arc of the story, okay? Do you have a question, Ken? All right. Okay, so first mountain building episode to build the Appalachians is right here, between Northern Europe and North America. The second one is coming from the back end of it with this volcanic island arc. That's going to lead to the future Acadian orogeny, number 2. The third one is behind it. They're coming in waves. And that's going to be when Northwest Africa comes in behind. So first boom, second boom. Third one is Northwest Africa comes in and builds up the Appalachian Mountains that we know of today. Okay? Let's see what time it is. We're going to go a couple more minutes. This is deep and heavy stuff. And there's the future Alleghania. So there's all three orogenies sort of laid out for you. Now, how long does that take to happen? Well, if this is the 458 million year mark, you're looking ahead by about another 100 million years or so, maybe 150 million years, is what it takes for all three of those to happen in succession and to come together to form supercontinent Pangaea. And again, some people don't even take the time to differentiate the different orogenies, but I wanted to kind of let you know kind of basically why does this matter? It's that the Appalachian Mountains, as we think of, did not originate from one single mountain building episode. It originated from three very different collisions, one with future Europe, one with an volcanic island arc, and one from Africa, and then a final one with South America that we haven't even begun to talk about yet. Juliet? What moving the continents? The plates. Yeah, I mean, you'd have to study these all kind of in order to kind of see the general trends. You'll see what I'm saying in a minute. For example, like these two, for example, one is kind of moving up a little bit this way. This one was down here earlier, kind of moved up and around. This one's going to kind of come up like so. They are it's complicated, and I definitely agree with you on that. Okay, why don't we take a break? This is a good time. We've been bending our brain a little bit on this. This great website. And what we're looking at here is the Cambrian period. What is this called? Biointeractive Earth View? Is that what? Yeah. And here, sort of this outline you can see is Laurentia turned up on its side. You can actually, I don't know if you can zoom in on that. Yeah, sure you can. That's Tennessee right there. You can see it turned up. And then notice that it's got some of the modern day cities and their placement. Now, I don't know what that's about because that seems a little off from where, maybe it's time zones or something. I don't know. Yeah, it's just weird because there's like, yeah, in North Texas, right. Okay, something's going on there, but that's a good idea. Cities. No, that's okay. It was a good thought though. So I'm going to leave you with this. I'm just going to show this to you real quick. I just think this is pretty awesome. Let me zoom out. And then we're going to look at, notice where Laurentia is. You know, it's essentially in the southern hemisphere. A lot of the rest of the Gondwana is on the back side of the planet over there. And what we want to kind of watch, here's Baltica. That's Norway right there. Here's Sweden. There's Finland, for example, probably northern Germany here. And this is Siberia. And what we're going to do now is fiddle with this over here to go forward in time up into the Ordovician. And so pointing out that tectonic orogeny, I want you to keep your eyes on Baltica, and it's moving toward Laurentia. And they should be moving toward one another. And now notice here, even way before it gets there, it's causing uplift of those mountains. Can you see that? And notice then some of those mountains are far south into Virginia and Tennessee. Not Tennessee, Virginia and North Carolina. So we don't have a lot of the tectonic mountains, as they were called, in the south. It was more of an impact on the northeastern part. So like, you know, New England, New York State, Pennsylvania, up into Canada. Now we're going to continue to move this because remember we laid out 3 orogenies in a row. You can see the first one beginning. Then we're going to focus on this landmass here, these volcanic island arcs and what they do. And that third collision is coming as Africa moves up into position. We're going to take it all the way forward and look at what happens when South America collides too. Okay, so here we go. We're going to go from the Ordovician period now. It makes sense because Ordovician rock is over Nashville. At that time, we were all in the ocean. That makes sense with what we see. Okay, so we'll keep coming north, but everything's shifting into the northern hemisphere. Now you see the Taconic Mountains are really well developed. And we barely enter the Silurian period. We keep coming up. And that's where we begin to focus on sort of this collection of mess right here. Let's take it forward just a little bit. Now, see what happens? That begins to really impact the mid-Atlantic and Southeast. And that brings in that sort of second wave, the Acadian, but it also impacts up here because it brings New England into place. It brings Nova Scotia. Remember, it was an island down here. It brings it into place. That's the Acadian orogeny. That's number 2, mountain building episodes. Whereas this one affected primarily the Northeast, this one affects sort of the East Coast in general. Now, we're going to have to come all the way up through. There's a lot of additional mountain building that's beginning to happen. And by the time we get into up into the Permian, that's where we're going to see the full formation of what's called the Alleghanian orogeny right there. So it's not what you might think, 3 very distinct events. It's a succession of mountain building that's a progression that eventually builds up a range that's about the size of the Himalaya Mountains. But notably, while the tectonics come up, there's enough time for them to wear down before the next mountain building. Okay? Then the Acadians come up, and then they wear down ahead of some of the next mountain building a little bit. And then the Alleghanies come up, and then they have worn down. So that's an important thing to be mindful of. Now, let's take this forward up just a little bit farther. And it's a little hard to see. Yeah, so this is South America right here. Here's Venezuela and Colombia, for example. Here's Brazil. And if we can back that off a little bit, I want you to kind of notice that part. Yeah, it's kind of hard to see. This is a little bit different, but this part eventually is what will come up and form the Ouachita Mountains right there over Arkansas. Okay. So anyways, this is just kind of a helpful viewer. You're going to begin to see that in a minute. More mountain building right there. And by the time we get into Permian and so forth, we're full into supercontinent Pangea at that point. Okay. Final thing, let's just look ahead to the breakup. All of that begins to be undone. Notice the Atlantic begins to open up again. But as it does, that old failed rift of the Mississippi Valley is still in place. It's still a weak point in the American continent. And it's going to stay there even when Pangea rips open again. And so that's still going to preserve that coastline of North America that's formed all the way back at the breakup of Rhodanium. Okay, I'm going to take that forward. You can begin to see the separation and the formation of the Atlantic all the way through the Cretaceous period. We've got dinosaurs in full effect now. And by the time we get all the way, the boom right there is where the dinosaurs go extinct. All right, we're going to have fun with this. I would encourage you to play around with this. It's really fun. Let's get back to the lecture. Jaron, thank you for showing me that. Any questions on any of that material? I see we got some things online here. Now we're good. Okay. Yeah.
Broken up, or do we all like it?
I want you to just kind of know the basic elements of the story. Taconic begins to impact northeastern North America. Boom, that's it. The Acadian is impacting the middle part of the Appalachians, and it brings in like Maine and stuff. The Alleghanian builds up the main body of the Southern Appalachians. And then when South America comes in, and I'm going to show you more slides to kind of get to this in a minute, but it'll collide from the south and it builds up the mountains all the way between Texas and Arkansas. Okay. Yes, Juliet. It's a great question. I don't know the answer to that. I think generally most of the major land masses that we have always been around. They've gotten sort of accrued to one another, you know, but I don't think we've lost any. All right, let me stop sharing here. Let's go back. All you guys online, are y'all doing okay?
Super duper.
Super duper. Okay, here we go. Let's dig in now a little bit. And let's see, I'm gonna have to sometimes navigating all this is a little tricky. Give me 1 second. I think I'm gonna have to pull that off of that website, right? Or off of that screen. Okay. We're going to come back over here and share that. That's what it did last night on me. It just gets a bit complicated to move things around. Hang on 1 second, guys. Let's see. Okay, and my class can't see that one now, so I'm going to pull it over here. Okay. All right, y'all able to see that online?
Yes, sir.
Got it. All right. Ooh, it's hot in here, guys. All right, y'all might want to do some stretching and kind of stand up and kind of get yourself rejuvenated here. We're about to go through from the Ordovician. We've left the Cambrian behind. We're going to go through the Ordovician and Silurian and Devonian now. And with this effort, we want to start looking, you know, a few of these processes that we're talking about. Again, if you get too caught up in the details, it could be tricky. I'm going to keep you focused on sort of the overarching sort of message here. So as we get in the Ordovician, somebody kick us off. Kian, what can you say about the Laurentian continent at this point in terms of what kind of rock you would expect here in Clarksville? Yeah. And, oh, well, and what would lead you to say sandstone? That's okay. Try it one more time. Let's say it's not sandstone. Yeah, limestone, right? We have a shallow ocean. Okay. It could be dolomite. It could be shale, but particularly because it's a shallow, extensive, shallow ocean. Look at how shallow that is over such a broad expanse, right? The Ordovician rocks here go all the way to Montana as a shallow ocean. There's some deeper zones like in Michigan and parts of Illinois there. And in those deeper parts of the ocean, you would expect things like shale to form. A little bit deeper waters typically would result in a different kind of depositional environment. Where you have some land masses like here, you might expect sandstone up against the edge of that small uplifted area of land. So let's take a look at how these small scale differences in these bodies of ocean and bodies of land, like what you might see in northern Alabama and southern Tennessee, let's look at those small scale differences and how they translate into the rock types that we see today. And more importantly, how we can see them expressed in the ecoregions that we recently covered. So here we have, for example, northern Alabama. Here's the Taconic Mountains that we saw earlier, maybe a little bit of the southernmost extension of those. There's a volcanic island chain at the bottom of that. We talked about subduction zones earlier. Again, I do not want you guys memorizing this stuff. But what I do want you to do is if you were to look at this image on your own at home, you'd be able to know what I'm talking about, right? You would not need me there to say, oh yeah, I know what a subduction zone is. I know what the Taconic Mountains are. I may not memorize it and remember it instantly from recall, but I want you to know how it broadly fits into the story, okay? So here's what we're talking about, this sort of different depths of the ocean. Limestone reefs over here are forming. There's corals over here. Indicated the present location of the town of Birmingham is right there. Notice the slightly deeper areas, right? Shale deposition. There's a couple of real key ecoregions we talked about with the Southern Ridge and Valley. There was one we said it's, remember this one? Say it with me. Southern limestone and low rolling hills and valleys ecoregion. Remember that long name? It correlates directly with this limestone formation. And what was the other region that's just to the east of that? Southern shale valleys. Here's where they form. A lot of that Ordovician and Cambrian age shale that we see today was laid down. Why? Because that part of the Ridge and Valley was slightly deeper ocean level compared to the areas with limestone. So let's look at some of the evidence for this. Here's some of that limestone that we see today. And if you were to look in that, you'd find evidences of coral reefs and all kinds of marine organisms. There's those shale formations. Again, they reflect different ocean depths. But we also see evidence in the general region in northern Alabama of the volcanic island arcs. Like this right here. This is down near Auburn, Alabama. This is what's called a granite pluton. A pluton is a giant, like, mass of magma that is it's sort of like a giant, it's just a solid mass of granitic bedrock that at one time was kind of buried under the land. And now, because of surface erosion, it's been exposed. Well, these plutons are associated with these volcanic island arcs. So if you know what to look for, and again, we're not geologists, we're not trying to be, but you can still see these plutons on the landscape and know that they are connected to these ancient extinct system of volcanic island arcs in their area. And because you have volcanic islands, not only do you have the original mass of the base of that island still existing from the plutons around, let's say, Atlanta, Georgia, right here, there's a bunch of these granitic plutons right in that area. This one's over here a little bit near Auburn. But if you have volcanoes, not only do you expect the igneous rock to sort of be there from where the magma is hardened, but what else does the volcano emit? Ash deposits, right? So we should then expect ash to be somewhere else. Can ash float over that open ocean? Can it settle into that ocean? Can that volcanic ash trickle down and sort of form a film at the bottom of the ocean floor? Yeah, you bet. If that ocean is 40 feet deep and it's a warm tropical lagoon, and you get, you know, an inch of volcanic ash that settles, it's preserved in that rock record. Well, we can see that. Here's a volcanic ash layer along Interstate 59, about halfway between Birmingham and Chattanooga. We can see the same layers in the rocks around Nashville. For example, around the I-440 loop that goes around downtown Nashville. If you know where to look, there's these what are called bentonite layers. Bentonite is the geologic term for layers of volcanic ash. Yeah, go ahead, Clayton.
Are these layers of ash deposits as thick as they are because the volcanoes that formed them were particularly large or active, or because they were active for such a long time?
Yeah, these are relatively thin, right? So these are sometimes just a few inches in thickness, right? They may have been thicker and then they become compressed over time. The biggest point I want you to, I guess, think about is that this layer is a testament to the fact that we had a volcanic island arc right just a couple hundred miles to the south of us. And those volcanoes were spewing ash deposits that were flowing over, that were blowing over and landing in these shallow seas, even here. So while we don't have igneous rock here, we have bentonite from the volcanoes just off to the east. Why is that important? Because it's part of that whole story of the mountain building process, right? Those volcanic island arcs are kind of ahead of that cluster of island chain, that Avalonia and some of those other things that are off to our southern edge there.
Hello.
Hello. Hey, Laura.
Yeah, on that ash, it's like, would it also indicate the quality of the water that was at that time? Because the ash was able to, like, maybe it was heavier and it didn't just dissolve, so maybe it was a higher mineral content in the water or something?
Well, I can't answer that. She was asking about, does that mean that the something about the water quality or whatever? I'm not sure about that, Laura.
Okay. But it said
yeah.
it was able to settle down to the bottom, go through the water and settle intact then.
Yeah, and just keep in mind, these oceans were shallow, warm lagoons, right? So they could have been anywhere from, 3 to 100 feet deep.
Gotcha.
Yeah.
Thank you.
Yeah. So here's what some of that ocean life would have looked like here during the Ordovician period. We have a lot of fossils. Here's some what are called graptolite, a type of marine organism preserved in some of the shale formations. That's named for Athens, Tennessee. The Athens Shale is a specific formation, but this is from Alabama, near Pratt's Ferry in Bibb County, Alabama. There's brachiopod fossils. So things like Asiatic clams are now modern day brachiopods here. This is near Fort Payne, Alabama in limestone. Here's some folks that are looking at a cephalopod fossil. This is a large type of marine organism, sort of has a horn-like structure that you can see in the bottom image there. There's a part of that cephalopod preserved that's sort of broken. Another section of that, you got a fossil sponge in the upper right. Also evidence of algae. These are algal layers called algal laminations, preserved in these chert formations. I've seen these around in some of the rocks of this area. So keep in mind, chert is also a type of rock that forms in shallow seas, as is dolomite and limestone. Fossil green algae. Okay. All right. So that's the Ordovician period. Now let's move ahead to the Silurian, roughly 400. So the Ordovician, if I were to ask you on a test, I'd want you to say something like, Ordovician is approximately 450 million years ago. Boom, that's the end of it. But if you said something like 450, 480, that's fine. I don't expect you to know the exact beginning and end dates. In fact, if you said 500, even though that's technically in the Cambrian, I'd probably still take it. I want you to know the stuff to a relative level, right? Imagine you're talking to an eighth grader, and you're explaining this stuff to an eighth grader. I want you to be able to carry that knowledge forward in story form like that. I don't want you to regurgitate a bunch of mindless facts. All right. Now let's before we go on, let's look at what were the key evolutionary events of the Ordovician period. Well, number one, following the Cambrian explosion 538 million years ago, by the time we get into the Ordovician, we have a sudden diversification of multicellular animal families. So we really see that diversification, and that's plainly evident from those marine fossils that we just looked at. But at this point, everything pretty much still lives in the water. Okay, most of life is confined to the oceans, probably also fresh water. Of course, there are rivers, but the land is barren. There's really not much going on with soil development, for example. It's a barren wasteland. But during this time, we begin to see the emergence of the first fungi and the first land plants, especially toward the close of the Ordovician and getting into the Silurian. Now, these first land plants are real small. They're just a few inches tall. And for those of you who have had Dr. Lebketcher for botanical diversity, some of those early land plants you might know as the rhiniophytes or trimerophytes or the lycophytes. Those are some of those early examples. I'm going to show you some pictures of them in a little bit. All right, let's look at some of the, land changes happening in the Silurian. We're going to pick up the pace a little bit because that first hour, I wanted you to begin to see all the nuts and bolts of stuff, right? Now let's sort of pick it up a little bit. Here we are in the Silurian, 430 million years ago, up to about 420. And the big theme here is that for a long time, the tectonic mountains, these northern mountains up here, are already beginning to build. Notice that 430 to 10 million years later, look at the amount of mountain building happening up here. That's that first orogeny right there, okay? That second one is going to be coming in a wave later from the southeast. But one of the things we begin to see is the continued now shift of mountain building from up here progressively more down into this region right here. See how much more mountains there are at 420 compared to 430 million years in the south? A lot more. Okay, so that's uplifting what will eventually be that Appalachian chain. As we watch this diagram in the bottom, you will eventually continue to watch that, and you'll see Africa continuing to come into contact with North America. Okay, there's that Iapetus Ocean basin that's beginning to close. Okay, we're still down south of the equator. We still got some volcanic island arcs, spewing lava and all that kind of stuff coming. Now, here's the middle Silurian period. Let me ask you a question. Do you think we have a lot of fossils in Tennessee from the middle Silurian? Why or why not? That's a great test question. Because anything above land, above ocean, is not preserving in the fossil record, right? Our fossils are primarily only in areas of depositional environments. And so you would not expect any of that to actually be preserving through being captured in deposits. You would expect anything that's above the ocean, primarily, most of that, to be eroding away, actually. You could, but keep in mind those fossils, as we'll come to see now, or those rock layers, are way down deep. So that's another part of the equation, right? You're going to find fossils where fossils are at the surface primarily, unless you're exploring deep sea ocean drills, 3 miles down. Yeah, you're seeing the fossils that come out of those different segments of that drill core. But if you're in West Tennessee, to get to the Silurian rock, you got to go down like 2,000 meters, whatever we talked about last class period.
So at what point, like geologic time, when you start to see areas that were on land be more preserved so that we can get land, plant, and animal fossils?
Well, the only way we get them is if they are in depositional environments on land, right? Swamps or floodplains. Those kinds of areas that would naturally preserve land, plant and animal fossils, but it wouldn't be like a mountainside or an open plateau surface or a hillside. Those will never preserve. So you only will find them. And that's why the fossil record is so skewed, right? It's really well preserved in species that live in wet areas. The species that live in dry sites, man, we have almost nothing in the fossil record because they don't preserve at all. Okay, so, all right. So here, photo of a geologist studying some sandstone beds rich in iron. These are beds deposited in shallow tidal channels and offshore bars. So again, sandstone, you can think about that near the beach, right along the edge, right? Here's some geology students down in Birmingham again, looking at this mountain cut called the Red Mountain Cut, collecting fossils from limestone. Here's another view of that same cut, which has an amazing display of rocks. And a lot of that red mountain formation is that reddish stuff right there that you see. Now, this is the same diagram. I'll point this out. It's pretty cool. This is really neat. Here, for example, you see the seam right here of red rock disconnected from there. That's a clear indication of a fault line where the uplift of the mountains has caused that rock to fracture and to break. You see several different faults that are visible there in that mountain formation. But notice that just in this profile, on the far sort of base of the mountain, over where Birmingham is located, you have Cambrian rock of the limestones of the Knox group. Then you have Ordovician Chickamauga limestone. You have still Ordovician Sequatchie limestone. And then above that, we have the Silurian layer. So it's all sequentially there, from Cambrian to the oldest, to Ordovician to Silurian, and what's coming next, what should be next in the sequence. After Silurian should be Devonian. And I'm not sure if it's here. Yeah, that ought to be the Devonian Chattanooga Shale, that real thin sliver right there. And then we get to Mississippian on top of that. A few more pictures of various kinds of scenes. A lot of this is Silurian rock, which is very red. There's a lot of iron present in the rocks of this period. Here's some folks that are studying these sort of Silurian formations. Picking out a coral fossil from the Silurian. So this tells you that a lot of this area still is under marine conditions. Here's a honeycomb coral from this time period. Lots of sponge fossils. There's the osculum, if you guys remember that from probably zoological diversity or biology 1120 when you study sponges that pour at the top of the sponge. More brachiopods. And then we have a clear unconformity where we have Silurian age bedrock here with trilobite fossils. And then right on top of that are Cretaceous age rocks. So there's a massive geologic unconformity here with lots of missing rock along the Tennessee River there in northwestern Alabama. That's the state of Mississippi across the river, by the way. A lot of fossils here, again, crinoids, trilobites, brachiopods, all kinds of cool stuff. There's a sea scorpion, 1.5 meters in length. Okay, with that, we've concluded the Silurian. We see that the Silurian is mostly, for this region, at least, a lot of marine organisms. Not entirely. There are some parts that are above land. And during the Silurian, as I showed you with the evolutionary chart earlier, we would expect to see the first land plants as well. Now, those first are what we know of worldwide. And that may or may not necessarily be representative of this region. So I'm going to show you here as we enter the Devonian, the amount of land organisms, land animals, and land plants is going to pick up dramatically during the Devonian period. Okay. Notice also what's happening in the world. Pangea is getting closer and closer to forming. These northern continents are getting larger. Siberia is up here now. Gondwana is still drifting up. And look at Florida. It's right there. All right. Now, as we get into Devonian, a couple of big events from an evolutionary standpoint. First, amphibians. By the way, it's worth remembering that we had first fishes way back in the Cambrian. So if you were to go to that American Museum of Natural History, for example, you'd see, let's not forget all the fish evolution that's happened during this time. Anybody here had ichthyology? Just if you can remember some of the major groups of fish, we can keep it very general. I'm not talking about like bass and eels and stuff, but like, yeah, you're okay. Give me the common name for that. Okay, so like the ray-finned fishes, and then there's give me some others.
Lampreys.
Fin fishes, the placoderms, right? Just in these big groups.
The
groups
lampreys.
go on to give rise to what else? What are some others? What are the cartilage fishes?
Are the lampreys in there with the jaw fishes?
I think the lampreys are in there. Are lampreys fish or are they the jawless fish? Right, yeah. The precursors to sharks, right? We can just keep this real basic. But all that's happening, all that's evolving after the Cambrian, through the Ordovician and the Silurian, so that by the time we get up into the Devonian, we have the lungfishes and the lobed fin fishes that all those evolutionary advancements have already happened, and our forelimb, literally our front limb originates from the first amphibians that would walk on land. And if you go to the American Museum of Natural History, Tiktaalik is one of the named fossils, which comes from Ellesmere Island in northern Canada. Is at least 10 years ago. I haven't kept up, but that was the earliest known of our ancestors to emerge from the sea onto land in an amphibious environment. It has every bone that you have in your forearm and your fingers and wrist bones and elbows. All that originates in Tiktaalik. So anyways, that's a big event. The first amphibians, the first jawed fishes begin to diversify during this time. Okay. And a lot of land plant diversification is happening as well. So we're roughly at 380 million years ago during the Devonian period. By this time, notice that a lot more of the land is beginning to build up here in the east. We still have this ocean off to this side. And getting back to what Clayton was asking about earlier, is like, man, is it the Tethys Ocean or is it the Theocraic Ocean? Here's the point, is there were two separate oceans, whatever we call that second. The first one was that Iapetus. It closed and brought with it that island arc that is Avalonian. The second one is the, I don't know whether to call it the Theocraic or the Tethys Ocean or whatever, but that second ocean basin is what is now closing behind it. Okay, so we had two oceans that come in and close. The first one's already kind of caught up in this mess. Here's the second ocean right here that's beginning to close. And then that's Africa on the other side of it right there. Okay, now let's stop and pause for a minute on the complexities that are happening over what is now the Mid-South at this point in the Devonian, okay? Remember how earlier we looked at North Alabama and we said, yeah, over here were volcanic island arch, there's some granite rock. And these deeper areas of ocean have shale. And these shallow areas of ocean have limestone. Now let's bring it forward several tens of millions of years, and let's look a little bit farther at a bigger scale, all the way from Iowa on the left to the Appalachian Mountains on the east. And what you'll notice here is that there's a lot of areas that are above land here, right? We've got some mountains off over here. And the creation of those mountains, as it lifts it up, on the other side is an area that is sort of being pushed down. It's being depressed. And there's a term for that, which we call a foreland basin. A foreland basin is a low depression or a low basin that forms when you have a mountain building episode. It's usually on the opposite side from where the collision is taking place. So if Africa is coming in from this side and you have a mountain range, you would expect the foreland basin to be on the other side of that. Now, that foreland basin, beyond that, so you come off this mountain, you go into a basin, it creates a ripple effect, right? So you might expect, while this is low, there's a high on the other side. Remember those anticlines and synclines? So this mountainous region creates a synclinal valley, more or less. There's actually lots of folding happening. This then is uplifted like a dome, like the Nashville Dome, okay? So it uplifts. Remember, this has been a low graben that there along the Mississippi River where the Illinois Basin is a graben because of the failed rifting from way back at like 700 million years ago. So that's a basin. So the point I'm gonna leave you with here on the slide is you've got these upland regions, right, where soils are eroding from. There's no fossilization taking place. You would never expect any fossils whatsoever from the Devonian period to ever be found here. Why? Because those rocks don't even exist anymore. The only rocks of the Devonian time that you're going to find, period, are the rocks that were laid down when they were in a depositional environment, in an ocean. So yes, we have Devonian rocks here, and here, and here, and here, and here. All those different basins have the rocks of Devonian age. They have fossils. if those waters were not too deep and if they were rich in oxygen. But if they were pretty deep, if they were very oxygen poor, then there might not have been a lot of life in those oceans. For example, has anybody here heard of the Gulf Coast anoxic zone? That's right off the coast of New Orleans, Louisiana, where the Mississippi River pours into the Gulf Coast. Because of all the pollutants, unfortunately, they're being washed down from a lot of agricultural runoff. It creates algal blooms that just sort of decimates the water quality, and there's not a lot of oxygen in that part of the ocean. So there's not a lot of life there. There's not a lot of fish that die and drift to the bottom that will eventually be fossilized. It's a pretty poor zone from a biodiversity standpoint. You did have a few of those in places, particularly in the deeper areas, where you just would not expect there to be much fossilization taking place. All right, now, what do you think is going to happen? So these ocean basins right now are filled with what type of water? I mean, it's salt water, right? So these are all marine lagoons. But as land builds up, what do you think those low-lying marine areas will turn into? Lakes, did you say? Maybe eventually valleys. What kind of, what do we say is moving on the land now? Amphibians, swamps, and what else is moving on the land? Amphibians and plants, right? So those two are moving on the land for the first time in Earth history. And you've got an abundance of water. It's salty at first, but eventually it's going to fill in, become low-lying swamps. And it's going to be fed by rivers that are washing off the mountains all around it, right? So this Appalachian mountain chain has rivers that are running down into it, forming alluvial plains and deltaic plains. And it's swampy, very much like South Alabama or Louisiana or the lower end of the Amazon. Okay. But keep in mind, we have very small plants at this point in the Devonian. We don't have giant trees yet. We're going to have them soon by the end of the Devonian. And we have amphibians. So those two together. Now, the final question before we proceed, and so it looks about like this. From an economic perspective, if you're in the United States, why do these areas matter? Why does the Arkoma Basin or the Illinois Basin or the Iowa Basin or the Michigan Basin, why do they matter? Coal, exactly. These are the coal regions of our country, right? That's where coal deposits are. And what is coal? It's the fossilized remains of swamps, okay? And notice how small and stunted these plants are in the foreground. These are things like lycophytes and trimerophytes and rhiniophytes. These are all some of those primitive, very primitive spore-bearing ancestors that are very distantly allied to ferns. And so, James, you're probably covering some of these in Dr. Lebketcher's class, I would imagine. If not yet, you will be toward this in a few weeks. Now, here's an exposure of what we call the Devonian Chattanooga Shale Formation. I've mentioned this a few times. Around here, you can see this when you're driving to Nashville and you drop off of where we live on the Highland Rim down toward like Old Hickory Boulevard on Interstate 24. You can actually see this layer right here in the upper part of this profile of Chattanooga Shale. This was laid down when this area was covered in a in a deep sea, relatively deep sea called the Chattanooga Sea. It was very oxygen poor, so there's almost no fossils in the Chattanooga Shale. I remember when I first became a professor and I found a deposit of Chattanooga Shale, and I was just like, I had my little rock hammer out here. I was nerding out there. I was like, dude, I'm gonna find a dinosaur up in here. And this is 15 years ago. I'm in almost in my 30s, right? And I'm chipping away, hoping to find like a dinosaur leg bone. And then it dawned on me, you idiot, you can't find a dinosaur bone because this is from the Devonian, buddy. This is like 200 million years before dinosaurs were even here. And when I finally learned that like 5 years later, I was like, oh man, I'm gonna find a fish off in here. And I'm digging around, and then I read that this is an extremely oxygen-poor rock formation. And so there are basically no fossils, but it is rich in uranium and radon. And as I mentioned, this is the formation that really helps to endanger a lot of people in this region. It's the second highest leading cause of lung cancer because this radon is this radon gas, which is invisible, you can't smell it, comes up under your basement, and it emanates from this rock layer, which is under a lot of people's houses. My wife and I was just talking about this yesterday. You can get radon mitigation systems in your houses, which are about $2,000. So you can have these put into your basement floor, and they have a way of like reducing the risk of radon pollution. So here's just a little segment here. You can see that Chattanooga shale right there. A lot of it is where it's so easy to break. It's so easily erodible that it's also just kind of pouring out of that hillside. If given 100 years, if you're to come back, this layer right here would probably be recessed into the hillside by like 3 feet, right? Because that's just pouring out, eroding really, really easily. And that's what's going to lead to the formation eventually, the continued erosion of that slope right there. Now, here's some evidence of those first land plants in here. You can see them in that scene from the upper left, some primitive land plants there. Shown in the upper left, these are old Devonian lycophyte fossils here from northern Alabama. Here's Eusthenopteron, a late Devonian lobed-fin fish, similar to our ancestor Tiktaalik. And again, I kid you not, that front forearm or fin has some of the same bones that we have in our front arms. In fact, tetrapods, the whole lineage of four-legged animals, evolved from this group of life. That includes whales, horses, chickens, humans, all come from that right there. Now, as you go forward in time, you begin to see the vegetation gets taller, you get more complex. Things like horsetails and ferns begin to evolve. Here's a general sort of, somewhat simplistic breakdown of the phylogeny of fishes, showing sort of the various major groups. And here's what we're talking about here. This lineage, the lobed fin fishes, is what gives rise to amphibians and eventually reptiles and mammals. So I do want to say, I know this these lectures here are a little deep, they're a little intense, maybe. But I want them just kind of to hopefully plug back into some of the other courses you've had, maybe reinforce some of the topics I'm sure you've covered in like general biology about, or evolution class or animal diversity or plant diversity, those kind of courses. And hopefully put it all into some kind of a sequence that makes sense. Preferably alongside this understanding of how the continents were moving and shifting and climates were shifting too. What do you think the climate of this region was like during the Ordovician, Silurian, Devonian, into the Carboniferous? Hot, humid, tropical, right? Now, compared to the Devonian, when we said the vegetation was short, now notice that by the time we get into the Carboniferous, 350 to 300 million years ago, we have full-size trees in development. Now, these are not trees as we think of them today. They don't have wood, for example. It's not the same kind of tree in terms of anatomically speaking. These are all trees that are more related to ferns than they are anything. And in fact, many of these are now extinct, like the extinct seed ferns, for example. A lot of their foliage is very fern-like. We have horsetails. We have just a whole wide array of plants. Now, at our school, of course, you would never be able to take a class to learn about all the wonderful diversity of extinct plants that lived in the Carboniferous. But if you were somewhere like Harvard or maybe UC Berkeley, you probably could have access to a paleobotany class, in which case they go through the rich fossil record and you learn about, all these different types of extinct plants. Also during this time, it's a major time period for the explosion, or what we would say radiation of insects. So we have a very large insects like very large dragonflies at this time. Some of them a meter across in wingspan. And then from this point forward, we're going to see the continued coevolution of insect life along with plant life. That's a big deal, especially as we get into the Cretaceous period. Keep in mind, we are still in what era right now? Carboniferous is part of what era? Paleozoic still. We got to get all the way to the end of the Permian before we switch off into the Mesozoic. Okay. So what are some first? Well, with the Carboniferous, we're going to call it Mississippian, Pennsylvanian. We see the first seed ferns. These are ferns that have the first seed, basically. And the seed is a very important evolutionary adaptation. The seed is a lot like the egg of vertebrate animals. If you think about like a reptile egg and how it differs from an amphibian egg, what would you say are the key differences there? It's watertight. Yeah, it's got a hardened shell, right? And what's a key, why is that an evolutionary adaptation over, let's say, a frog egg? What is it again? It's adapted to dry land, right? So what's a key difference between the spore of a fern or the spore of a moss and the seed of a seed plant? It's got a protected seed coat to protect it from drying out on land. So the egg and the seed are both parallel evolutionary adaptations. One for reptiles emerging from amphibians, and the seed from seed plants emerging from non-seed bearing plants. What's driving this emergence of these two features for adaptation to the dry conditions of life on land? What's driving that adaptation?
Photosynthesis.
Again?
Seeds regress.
Well, seeds evolving for the first time ever during this time, just like the enclosed egg is of
The seeds, the water.
or the seeds regressing. I'm sorry. Yes. Okay. Yeah. In a way, they are going to be regressing. Right. There's going to be fewer and fewer areas covered by oceans for sure. There's a lot more land mass. Okay. So let's get into that. Here we are in the early Carboniferous. Now, keep in mind, we've not reached the Permian yet, which is the real period by which this third orogeny takes place, okay? We've already gone through the Taconic and the Akkadian, and now we are experiencing, as we speak, in the Carboniferous, the uplift of the full Appalachian Range as part of the Alleghanian orogeny. Now, how is this taking place? Take a look at Africa over here. North Africa, underneath the modern-day Sahara Desert, at this time, 350 million years ago, is still very much in an ocean environment, a shallow ocean. But as this landmass is moving northwest, carrying Florida with it, it's now making impact, closing that Rheic Ocean, that second ocean basin, and making impact with Eastern North America, particularly the southeastern portion of North America, what we think of as the Southern Appalachians is being impacted. Not as much impact up there with, say, Eastern Canada or New England. Now, two things are going to happen. First, Africa's coming from this direction, and after it makes a collision, then there's going to be a rotation like this, clockwise rotation. And it's that clockwise rotation which is going to bring South America up for that second bump. And that second bump is what's going to create the southernmost and westernmost extension of the Appalachians, which today are in Arkansas, Oklahoma, all the way out to West Texas. There's a range of mountains in far West Texas called the Marathon Mountains. And they're all the result of that second bump coming from the south with South America. Now, We still have Gondwana and we still have, what's now known as Euramerica. I don't really care that you know that, but Euramerica basically is the combination of Laurentia, Baltica, and Siberia all together combined to make the northern supercontinent Euramerica. And then that's gonna collide with Gondwana to form Pangaea when that happens. Couple things. Start taking note of the colorations on these maps. What do you notice about most of the map here in terms of its color? It's mostly green, which indicates a lot of plants on land. Okay, that's by design. The areas that you see in yellowish or yellowish brown are thought to be areas with not a lot of plant cover. And why could that be? Why might you not have a lot of plant cover in those regions? Yeah, it could be dry. You could have the very center of a large continental landmass, right? Like right here, meaning that the ocean currents they don't have enough moisture to carry all the way inside to that landmass. Think about like the modern day Gobi Desert of China. It's so far in the interior of China and Mongolia that there's no amount of rainfall that can get there from coming from the Indian Ocean or from the Pacific Ocean. It's in the middle of a continental mass, which makes it naturally prone to being a desert. So you could have that situation. You could have other kinds of situations like maybe very drying winds coming off of an ocean, for example, absorbing all the moisture from a given environment. Kind of like the Atacama Desert in Chile and the coastal deserts of South America, or the Namibian Desert in Southwest Africa. Okay. So not everything is going to be covered in vegetation. And then what's one other big feature that you notice that maybe we haven't talked about yet so much? What's over the South Pole? It's a big glacier, right? A big ice cap that's developed there. Okay, now let's move it forward in time. So here we are around 345 million years ago. If we're tracking our diagram, then we can see that second ocean basin, the Theocraic, we'll trust that's what the name of it is. That second ocean basin is closing. And then this over here on the other side is what little remains of the former Iapetus Ocean is on this side of that ocean trench. Okay, so it's already closed. It's already been closed. In fact, it's jumbled up. The middle of that former ocean is right in the middle of what we call the Acadian suture, where these land masses have now buckled into one another, and it's totally eliminated that former Iapetus Ocean. Okay. Now we have sort of here's Africa now coming up. There's Florida. It's all beginning to collapse and collide. And as we go forward, you're going to begin to see this area change a lot. And you go from what was very sort of shallow ocean with different parts of sort of deeper basins. This is going to begin to sort of ramp down into some deeper water there. 330 million years, it's almost closing up that Rheic Ocean. Now, let's zoom in and let's begin to examine what's happening right over Tennessee and Alabama, northern Mississippi at this time frame. So keep in mind, what is just east of Clarksville, Tennessee at this point? Well, first of all, what is the area right at Clarksville at this point? It's either underwater or on the edge of an island, right? It's pretty much underwater here. But there's an island just off to the east. But if you go even farther to the east, over along what is the current day border with North Carolina, what's there? There's a coastline, and importantly, there is a mountain range, okay? The remnants of the Taconic Acadian mountains are coming south. Those mountains then have rivers bringing as those mountains are rising rapidly. The faster they rise, the faster they erode. And so that material, as it's eroding off the mountain, is filling up these basins, these depositional basins with things like sand, which becomes sandstones, or, the other types of rocks that we mentioned. Okay. But let's look at this in a very focused view. Here's what we can see. Number one, off over here to the east, where there are these mountain ranges, there's one of those rivers coming down, and notice that there's a delta there. There's a river delta. So we would expect in that kind of floodplain environment, what type of sediments are being laid down in a river delta? What is it? Silt. Very good, Juliet. And silt, once it compacts and solidifies, is going to form into what type of rock? Siltstone. Remember we talked about the tooth test? With claystone, you can scratch your tooth and it's very smooth and it doesn't scratch. But you could scratch it with some siltstone, it's going to like pull some enamel off of there, right? You can feel it. It's gritty. So you would expect a layer of siltstone to be laid down where that river delta is. Now, this is very much like if you were to step off of the Louisiana coast into the Gulf of Mexico at this point. Then you've got an area of somewhat shallow limestone, shallow seas, where you're going to expect charty limestone. Now, this is the Mississippian period. This is the rock. When I held up this app earlier and I said, hey, what is the rock type over this region? What period did it say this is? Mississippi. And in this case, it said it's the St. Louis limestone. But if you're in many parts of southern Middle Tennessee, you have a chert layer there, the Fort Payne Chert Formation. These were all laid down at this time in shallow seas. Now, who can remember what we call that little east-west chain of, it's a low mountain ridge that runs east to west across northern Alabama. It's got its own ecoregion name. It's a very short line of little hills. Who remembers it? We said that it's notable because it's one of the southernmost places for eastern hemlock trees and sweet birch trees. And it's got some little cool canyons in it. No? Anybody remember? Anybody on the computer remember here? Let's see. Let's check the chat box. Who knows what that little region in northwest Alabama is called? A little line of hills.
The fall line?
No, not the fall line. When I told you about this line, remember I brought up my friend Kyle Leibarger and showed you that YouTube video?
Yeah, the Hartsel stuff.
Yep.
Yep.
The rock type is called the Hartsel Sandstone. Check it out. It's during that time that these barrier islands, think about these coastal islands right off the edge of the coast. Those barrier islands were forming, laying down deposits of sandbars like you might go out and visit right off the coast. Those barrier islands today are still preserved as that east-west trending ecoregion we call the Little Mountains ecoregion. And that's it right there. The Little Mountains ecoregion. It was a chain of barrier islands at this time.
So cool.
So cool, right? Okay, now, last thing I want to point out is you've got other river deltas coming in from the south. Why? Because this is most likely South America. It's almost up. This is the remnants of the Rheic Ocean about to completely be eliminated. All this is going to do is continue to sandwich together like this. You got a deep ocean trench up here. This is South America now coming around for that second bump. Here's Africa. Notice the force coming from this way. And then this is South America about to bump up into Arkansas. So in these areas where you have swampy river deltas, that's where you have these magnificent forests of the Carboniferous age, big coal swamps. growing down on those deltas and those river floodplains. Very swampy conditions. Why does that make sense? This is the Warrior Basin. This is one of those basins that later would become a major coal producing area. And some of this, because it is on land, like in a river floodplain, we would expect to go there and find fossils from the Mississippian of species that lived on land, like trees and reptiles and salamanders or amphibians. And we're going to show you some of that in just a minute. But right off of that, where you have Mississippian, the area is covered in a shallow sea, for the same period, you would expect to find limestone fossils. That's what you see here in Middle Tennessee. So in Middle Tennessee, all of our fossils from the Mississippian period are limestone or chert. But you go to parts of Kentucky and northern Alabama, Mississippi, you can find Mississippian sandstones and Mississippian shale. And those have fossils of land animals and plants. So here's some of those formations. So this is an ancient barrier island right here in North Alabama at Cane Creek Canyon in the heart of the Little Mountains ecoregion. Those are the sand dunes that are still preserved right there. Now, I can't read the clues, but a geologist could go and read all the clues in those layers of sand. Just like if you were to go to a beach dune that is sort of eroded away, you'd be able to tell where various wave action has deposited those dunes. You can still see the signatures in all these rocks. Okay, some of these areas go from sandstone into shale, indicating those lines of transgression and regression at the same place, indicating ocean levels were changing at a very fine scale over a short period of time. Going from sandstone to a coal seam, you know, it was a tropical floodplain, swampy floodplain, going down into carbon-rich shale. So here's a paleontologist, a paleobotanist, studying plant fossils here in North Alabama. And here's some of this is a tree trunk of one of these called a lycopod. These are called the scale trees. They have this sort of diamond shaped, almost like a snake skin pattern to them. There's a cone of one of them in the upper left there. This is in Colbert County, part of the Little Mountains, right there, part of that barrier island chain. Here's an exposure of some of the marine shales in around Birmingham. So that area was under a shallow ocean. Here's an area of exposed Mississippian limestone. This is all oceanic material, showing that right in that same area, all in close proximity, you can go from total ocean conditions to land conditions in the span of 10 miles or 20 miles.
Good question.
There's crinoid fossils. Many of you have picked up crinoids along creek banks, I'm sure. And there's some more parts of the crinoids. These are often called sea anemones. Those are sort of the flowery looking heads, but they're actually animals. Bryozoans. Tropical coral reefs. Horn corals. Shark teeth. Colonial corals. And a lot of these today have an economic benefit because these limestones, if you go to almost every area where these limestones are prominent, there's a Vulcan rock quarry there. So these corporations are using these to make cement or the crushed limestone for highways. A lot of these are manufactured into various products. The lime is used to fertilize agricultural fields and to make them more alkaline. So we owe these ancient seas and the geology that they have to a lot of our local economy. All right, that's the close of the Mississippian period. That's the first and oldest of the two in the Carboniferous. Now what we want to do is let's get into the younger Pennsylvanian period. This is really the height of the coal age. This is when the biggest and most robust swamp forest existed. The insects get bigger even still during this period. And this is a relatively short time period. This is 323 to 299 million years, just about 24 million years span of time. Now, notice by this point that that mountain range was the size of the Himalayas has gotten dramatically longer and wider. I mean, it's a great distance across those mountains. So, again, these were the size of the Himalayas. The Gondwana is down to the south. What do you think is driving a lot of the sea level change that we've been talking about for the past little bit during the Mississippian? Yeah, the glaciation, right? And how does that work, Kiki? So talk me through what's the correlation there? So more water locked up in glaciers means that global ocean levels are going to go down, right? And if you don't have glaciers, then sea levels are going to rise. One of the greatest fears right now is that we're going to melt the glaciers of Greenland and Antarctica, the two Arctic ice sheet, the Arctic and the Antarctic ice shelf, that they're going to melt more rapidly than they ever have in history. And people often say, well, why is that a big deal? I mean, hell, there's been a glacier down there before, it came and went, but there were no people alive, right? There was no one alive. Humans ain't gonna be around for another 294 million years. And that's human ancestors. We're talking about getting back to shared ancestors with chimpanzees. We got to go almost 299.5 million years before we get people on. And so it matters because these kinds of changes in sea level were happening over tens of millions of year time frame. What we're talking about is sea level change happening in the span of a single or 2 or 3 human lifetimes. There's not enough time to change. There's not, I mean, I don't want to sound dire, but there's not enough time to respond. If we don't figure out a solution, cities like Miami will be underwater by the year 2100, at least large sections of the city. Large sections of downtown New York City. I mean, we thought Hurricane Sandy was bad when salt water infiltrated the subway system and shut down stuff. We ain't seen nothing yet until the Ross Antarctic shelf begins to totally collapse in, and we see 100 to 200 feet of sea level rise. That will be detrimental. Now, will we in Tennessee suffer from that? Not from inundation, but the people of Palau and Micronesia and, you know, all the Polynesian islands, they'll be totally underwater. You know, the people of Yucatan Peninsula, Mexico, they'll be totally underwater. People of Rio de Janeiro and Sao Paulo, Brazil will be totally underwater. And what we have to think about here in the interior of Eastern North America is when they get underwater, where will they go? We will begin to see people move and migrate at scales we've never seen before to flee coastal regions that will become inhospitable and inundated. And if we think habitat collapse is already severe enough and biodiversity deterioration from habitat loss is severe enough, we have seen nothing yet. When the people from South Florida flee, and we're talking about our own citizens in this case, when we talk about our own South Florida citizens begin to flee to move to Tennessee because there's more sea level, or people from coastal Virginia or Washington, D.C., it's going to create upheavals and migration patterns among our own citizens. Then you compound it with the challenges at a global level of people needing to flee entire countries to go other places as environmental refugees. So the key difference is here it's taken 10, 20, 30 million years to see those changes. We're talking about seeing those changes by the time your children get old enough to die, you know, as old people. Like my youngest boy right now is 9. If he were to live to be 100 years old, and let's say he dies in the year 2114, then very likely by the end of my son's life, much of the Everglades will be underwater, right? That's the kind of rapidity that we're talking about happening. So just want to put that into context. Now let's see, what are some of the things that we want to talk about from the evolutionary perspective with Pennsylvania? Well, we have much bigger trees, bigger insects, And we also then are seeing, we've already hit the highlights of some of these, like first reptiles and so forth. Let's take a look here, just bringing it back to Tennessee. If you're keeping track of where all this stuff is, here's this large area is Mississippian rock at the surface here in blue. This is the area that's higher up on the top of the Cumberland Plateau. That is mostly the Pennsylvanian aged rock. I've got a question there, which is where do plant fossils occur in Tennessee, and from which geologic time periods do they represent? And so if you want to find plant fossils from the Mississippian, we don't have any, because all of our Mississippian rocks are oceanic in nature. If you want to find Pennsylvanian rocks, though, you can find those. We do have plant fossils from the Pennsylvanian, which are 300 to 350 million years old. If you want to find fossils of Cretaceous age, then you're out here in this part of the state. And likewise, if you want to find dinosaurs, the only place that one's ever been found is right in here. It's the only place where those rocks exist. All right, we talked, again, these mountains are growing. We get the picture there. Look at the diagram in the upper left. It's all come together now. Africa has finally collided. But importantly, look at all the stuff geologically that's happening. All of these represent various islands that have been pushed into each other. Island arcs and small terrains like Avalon. All of this has been thrust together when it used to be separate chunks of land. That's basically how we built Eastern North America. And of course, you know, we've got Florida right there is the northwest part of Florida, which is part of Northwest Africa. So we talked about some of these deltaic plains. Again, we still got extensive rivers coming into this region that is Middle Tennessee, extensive coal swamps. You can see some of the elevation here, some of the differences, some of the types of rock. We don't have to spend a lot of time on this. I do want to point out what's called, in your book, talks about this, the Mencken Paleozoic footprint site. Why is that important? Why? Because those are the footprints of one of the earliest reptiles, maybe an amphibian, and it's on the bottom or the lower end of a floodplain of an extensive swamp. I'll show you what those look like. This is just to the northwest of Birmingham, in that big area that we call the Black Warrior, the Black Warrior Basin, which is known for its coal formations. So I'm going to go past some of this here. But this is probably what it was like just off of the slopes of the Appalachian Mountains. They were very high mountains at that time. They would have had alpine zones at the top, tropical forests coming all the way down to the edge, deltas, river deltas coming out into the ocean. Again, giant tree ferns and seed ferns, amphibians. A lot of coal formations today from these regions, very important economically for us. And now let's take a look at some of these plant fossils. Right here in this, this is DeSoto State Park in northeastern Alabama near Little River Canyon National Preserve. Right there at the top of the waterfall above DeSoto Falls is the fossilized wood from a tree from the Pennsylvanian period. You can see a couple of those inset photos right there. Here's another one. This is in a coal swamp in northwest Alabama. The entire trunk of a early Carboniferous Pennsylvanian age tree is preserved. This guy right here, he's just chilling with his Mountain Dew, right? Check out that tree trunk that he is sipping on his Mountain Dew while he's digging that thing out. So some great fossils here. Your book is really very richly illustrated with a lot of these. Let's talk about one concept real quick called a form genus. Do y'all know what that is? Form genus. So imagine the challenge you have as a paleontologist, particularly being a paleobotanist. If you're out studying a particular fossil location, let's say you're Mountain Dew man, And Mountain Dew Man goes out and he's digging here and he finds this tree trunk, right? He's like, wow, that's really distinctive. He studies the surface texture of that tree. He looks at it under microscopy and sees very distinctive patterns to that. Of course, you can't get DNA or anything out of this, right? It's way too old. But he's studying it from a morphological, outward physical appearance. In some cases, you could do some limited anatomical work, maybe cross sections of structures and stuff. But then imagine he goes over, let's say to that side of the quarry over there. And in that same hillside, a few hundred feet away, he digs out a branch that has some leaves on it. You can imagine that, especially in the early days of paleobotany, they didn't have a way to know if that branch with leaves is the same species as that tree trunk, right? Because they're separated now in space. Because what are the chances you're going to get both a tree trunk with its branches and leaves on the same thing? Carry that one step further. What if you now go and you dig in another place and you find a cone or flowers? How do you know they go with that tree trunk and with those leaves? You don't. So what paleobotanists do is they describe things called a form genus, basically saying that, hey, this tree trunk is in the form genus Lepidodendron. This branch with leaves is Lepidophyllum. So they give it a name that sort of, it basically is intended in paleobotany to say, we don't know how these things are related. And so I'm going to stop there, but I just want you to kind of know that that's actually a thing in the world of paleontology, particularly paleobotany. So this, for example, illustrates that. All right. So here's the trunk of Lepidodendron showing that distinctive diamond-shaped scale pattern. That's the form genus is Lepidodendron. But the wood, which is fossilized from the inner bark, is called Noria. It's probably the same thing, but they didn't know that when they discovered these two 100 years ago. It's only that connection's only been made more recently. Here's the spore case, which is Lepidostrophyllum. Okay. Here's the root systems now assigned to the form genus Stigmaria. And then the fossilized leaf, Lepidophyloides, is the leaf. All of these are different parts of what we now think are a single ancient extinct species. But each of these we call a form genus. Here's just some other examples of some really cool fossils found from this region, like, here's more brachiopods, of course, different tree parts, leaf sections, etc. A lot more of that. This is what their modern relatives look like. So today, those giant trees, what we call lycopods, those giant trees that had sort of those scaly looking leaves, all the big relatives have long since died out. And all we have left on this earth are small representatives. Like this one's about 6 inches tall. That's about as big as they get. These are all living examples today in our forests of those lycophytes. We also have living examples of the horsetails. So notice this sort of this jointed stem that has these longitudinal grooves on it. Well, I'll show you what that looks like today. That's called horsetails. We have them around. They occur on creek banks and swamps. But likewise, both of these cases used to grow into like 100-foot tall trees. Today, in all these cases, they only grow to just a few inches tall, maybe a couple feet tall. We had a lot of fern-like plants, these coal plants, various types of ferns. These are all found fossilized. Parts of various fossils of wood tissue and pith cavities. But we do have some animal fossils here, like these horseshoe crabs, suggesting that this area was right along a muddy coastline. And you can see that tail drag mark in that example. Here's some millipede prints. You got some insect larvae traces. There's the wing of a dragonfly. By the way, that's named for the author of your book right there, Lacefieldia. And then we have the footprints of a primitive reptile-like creature. Also, they come from the Mencken fossil site. And you can see those little footprints there. So we have land at that point. Here's a larger Paleozoic footprint of an amphibian. Frogzilla handprint right there. Okay, small footprints of an amphibian there on the left. Okay, and by the late Mississippian, again, we are fully mountainous. And this is what the region over East Tennessee and North Carolina looks like. And the highest mountains of this chain are over what today is the Piedmont region of Charlotte and Chapel Hill and Richmond area of North Carolina and Virginia. And that big high range of mountains, probably 25, 30,000 feet in elevation. Today, it's almost flat. At most 1,000 feet here or 500 feet there. All that's been lost and completely eroded down in the past 250 million years. Now, what that means for places like the modern day Himalaya mountains, here's India, right? Bangladesh. This is the uplifted Tibetan plateau in the Himalayas. There's the Gobi Desert. All that's going to be gone in probably 60 to 80 million years is what it will take to erode those away. Now, the end of the coal age, as we call it, the end of the Pennsylvanian, there's a distinctive long period of time that's now missing entirely from the record. We talked about this early on. 200 million years is gone from the record. And this is what creates an unconformity between these Paleozoic rocks of the Pennsylvanian, and this is the Cretaceous rocks here. So why don't we have that anymore? What led to all that disappearing? What do you think? What's that? It's erosion, right? I mean, look at those mountains right there. There's no depositional environments left, right? It's all steep mountains. Those completely washed away down to their bare roots. And it took place during the end of the Pennsylvanian, through the Permian, through the Triassic, through the Jurassic, to the early Cretaceous period. All that rock eroded away. And importantly, it was also during this time is one reason why, for example, the period we're about to come to, we're going to see is the, I don't want to give it away, so hang tight here. Yeah. Notice how at this point formation, now we have Pangea is fully assembled, right? Everything's together. What do you notice about the continents now in terms of their color patterns? A lot of browns, not much green, right? That's because we now have massive, widespread continental conditions. We have mountains. We have a lot of dry conditions. This is the beginning of a major episode that lasts many, many tens of millions of years of very dry conditions, leading to the largest widespread expansion of deserts ever. And why does that correspond with what we talked about at the very beginning of this hour? What two groups benefited from dry conditions? Reptiles and seed plants. And what two groups were adversely affected by drier conditions? Those big fern spore-bearing plants, right? Their spores need a lot of moisture. So we lost all those to extinction. And a lot of amphibian groups also went extinct during this time. So it favors those that have protected seed coats or shells. And that's why we see this next period, the Permian, is the age of reptiles. That's when reptiles radiate as a group and become a major force on the landscape. Now, we can see a lot of evidences of this time of Pangea's formation in our rocks. Like these are folds, for example, where these rocks are being crushed, and you can see a thrust fault here, for example. Lots of evidence. We don't need to get too deeply into this, but you can just see a lot of evidence from the faulting and cracking and folding of the rocks. It's extremely complicated. Let's just take a look at this one image right here. Okay, this is near Birmingham, Alabama. And you can just see all these layers of rock that have just gotten jumbled and twisted. But look how deep this is. Right? This is sea level right here. 17,000 feet below the surface is the Cambrian Conasauga Formation here. But up near Knoxville, that formation is at the ground level. Okay? So in some cases, things like the Knox Group, which is named for Knoxville, Tennessee, those limestones in Knoxville are present at the surface. But at this particular location, just in St. Clair, Calhoun, and Talladega counties, Alabama, just east of Birmingham, these are between 11,000 and 14,000 feet below the surface. And it has to do with that major faulting and folding and mountain building that kind of creates, see, that's like a dance, you know? All right. So huge amounts of land deformation. And a lot, not only is a lot of that, you know, upturned, some of it's vertical, some of it's folded back onto itself, but then look at all the land that would have been above it that is eroded away. See the angles of those rocks, right? You can see how much of that has simply been eroded away. Imagine, this will maybe help you to imagine what we've lost. You can see the layers of the tilts of the rocks. It's like that's all been just totally scraped away and eroded away. Again, you can see the angles. Many thousands of feet of rock have been eroded away on the northwest side of this ridge. That really says it all with that. Several miles of rock eroded away. It's an unfathomable amount of landscape change, isn't it? Just to think, not only how much rock we've lost above you, but how much rock is jumbled under your feet for literally, I mean, it's like a mountain the size of Pikes Peak, Colorado, underneath our feet that just goes down and down. All that rock lost. We do have some ice ages we've talked about. And now we enter the driest period, which we talked about as the Permian. And this is the period we'll probably pick it up next time. Let's see. Let's stop here.